That was an interesting conversation. Next, we have on-device training, and we'll have Shama from Microsoft take us through on that.
Do you have the clicker? Here. Okay. Thank you. Good morning, everyone. Let's discuss on-device training now. I'm Kshama, and I'm from Microsoft. I'll also have Beju with me on video. And we are both from the AI platform team at Microsoft. So let's dive briefly into the motivation for why we need on-device training for with ONNX Runtime. Before that, outline, motivation, scenarios. We'll do a tech deep dive briefly, and then we'll take questions in the end. So motivation, assuming that I'm an app developer, I will have my apps running on multiple devices across different platforms, maybe even using different frameworks. And I have a lot of data that's being created across these devices. I would potentially want to use this data to enhance the end customer user experiences. However, these devices are resource constrained. So it could be a laptop, it could be a mobile phone, and it may be resource constrained in terms of battery life, in terms of memory, in terms of even the shared space that I have to have with other applications that are running on the device. And of course, privacy is very important. So I want to make sure the data does not leave the device. And the training that happens to enhance these experiences is all local. I also, as a developer, want portable solutions. I want a solution that works across frameworks. I want a solution that potentially even works across different platforms like cloud, desktop, mobile, etc. So what the on-device training solution provides is using ONNX Runtime. It is an efficient framework-agnostic local trainer that trains with device data on the edge. So let's break this down a little bit. It's efficient because we've strived to make it both performance and memory efficient, including to save battery life. We've also made it framework agnostic, so it starts with an ONNX model. As long as we have an ONNX model, maybe from, if you're using ORT inference, you already have an ONNX model, or even if you're using other frameworks, you can convert it to ONNX and it's ready for use. And it's local. The data is not leaving the device. It's all the training happens on the edge. It's preserving the privacy for your end customers. And it's training on the edge. So this is using all the resources, the limited resources, including CPU. So that's as long as you have a CPU on your device, you can train using the data on the edge. So quickly, we'll touch on the scenarios. The major scenarios are federated learning and personalization. So personalization is where you fine-tune on the device. Typically, you'll enhance your inference model and train it with local data, make it serve your customers so that it's just giving them a richer user experience. We have federated learning, which is more training a global model. So you train on the device, you send the model differences up to a global model, which is potentially in the cloud, and then you update that model with all the necessary changes from the edge devices without the data again leaving the edge devices. We touched on a lot of the key benefits before, but I just want to reiterate that this extends the ORT solution. So ORT inference, again, if you're already in the ecosystem, this provides an end-to-end flow from inference to training and back to an inference model that you can run on the end user's device and again, give them a better experience. So with that, I'll jump into our video presentation, in which Beju will take us through a tech deep dive, and he'll also show us a demo for ONNX Runtime.
Hello, everyone. I'm Beju, and I'm thrilled to be here representing the AI Frameworks group at Microsoft. Over the past few months, our dedicated ONNX Runtime training team has been hard at work developing an innovative solution for training ONNX models on edge devices. Today, I'm extremely excited to showcase the incredible progress we've made. On-device training allows us to train models directly on edge devices, such as mobile phones, web browsers, and gaming consoles, all while ensuring the privacy of end users. The ONNX Runtime's on-device training solution builds upon the robust ONNX Runtime inference framework, providing a memory and performance-efficient way to train models without significantly impacting power consumption or battery life. Now, let's delve into the process of learning on an edge device using ONNX Runtime, which is divided into two phases. First, we have the offline phase. In this initial stage, training artifacts are generated using Python in an offline script on a server or development machine. These artifacts include the training ONNX model, the evaluation ONNX model, the optimizer ONNX model, and the checkpoint file. Next comes the training phase, which takes place directly on the edge device. This is where developers interface with ONNX Runtime's training API and define the logic for the training loop. To better illustrate these two phases, let's work with an example. Imagine we start with a simple ONNX model that consists of a linear layer followed by a ReLU activation, followed by another linear layer. For this example, let's assume that we want to train only the second linear layer in the model. By passing this model to the ONNX Runtime Python utility, along with the names of the model initializers we intend to train on the device, we can generate the necessary training artifacts. One of these artifacts is the evaluation ONNX model, which is essentially the input ONNX model with a loss node attached. This node, in this case, is the softmax cross-entropy loss node, serving as a crucial component for evaluation. Another artifact is the training ONNX model, which incorporates the gradient graph of the input ONNX model on top of the evaluation ONNX model. The training ONNX model outputs the gradients for each of the trainable initializers, allowing us to focus specifically on the parameters associated with the second linear layer in this example. To avoid duplicate definitions within the training and evaluation ONNX model, the checkpoint file abstracts the shared model initializers into a binary checkpoint file. Lastly, we have the optimizer ONNX model. This model takes the trainable model initializers and their computed gradients, effectively updating the model parameters in the direction of the gradient. Now that we have these training artifacts in place, we are ready to deploy them and enter the second phase of on-device training, the training phase. ONNX Runtime offers a wide range of language bindings, including Python, C, C++, C#, and Java, with Objective-C and TypeScript bindings currently in development. Packages for Windows, Android, and Linux are already available, while packages for iOS and web can be expected soon. The entry point for training is the training session, which takes all the training artifacts as inputs and exposes methods that enable developers to train their models effectively. These methods include train step, eval step, optimizer step, reset grad, and more. Once the model has been trained on the device, the training session also offers a convenient way to generate an inference-ready ONNX model directly on the device itself. The inference ONNX model can then be used with the inference session to perform inference tasks. Now, let me demonstrate the power of on-device training through a practical application. For this demo, we have developed an Android application that utilizes the MobileNet v2 model. We specifically select the last classifier layer to be trained, and we use the model to learn to classify celebrity images. This idea can be extended to tasks like tagging images of loved ones from their gallery. In our demo, we will be using images of 4 popular celebrities: Tom Cruise, Brad Pitt, Ryan Reynolds, and Leonardo DiCaprio. Initially, the model has no knowledge of these celebrities and randomly predicts their images. However, as we start feeding in images and labeling them, the model begins training. We intentionally provide 16 images per celebrity, reserving a few that will be used later for inferencing. Each input image is pre-processed batched, and fed to ONNX Runtime's training API, which updates the model parameters, allowing it to learn and make accurate predictions. This training process occurs for 5 epochs. At the end of training, ONNX Runtime seamlessly transitions from training to inference. Now with the model fully trained, we can begin inferencing. As you can see, the model has successfully learned to classify the celebrities using data that never left the Android device itself. In closing, I want to emphasize the immense potential and impact of on-device training with ONNX Runtime. This approach enables us to bring the power of machine learning directly to the edge devices, providing an efficient way to train models while safeguarding user privacy. Developers can unlock new opportunities for personalized and intelligent applications. Whether it's image classification, voice recognition, or natural language processing, on-device training empowers us to create smarter and more responsive experiences and can be used in a plethora of scenarios, such as personalization and federated learning. Thank you all for your attention and for joining me on this journey into the realm of on-device training. I invite you to explore our work by visiting our GitHub repository, where we host the code for this demo. Thank you once again. That's all for now.
Thanks, Beju. So as Beju mentioned, we have a lot of resources. I've listed it here in the slides, and I invite you to check out the repo, contribute, reach out to us if you have questions. We again, as he mentioned, we have a large number of language bindings that we support: C, C++, C#, Python, Java. We also have JavaScript, Objective-C, and Swift coming up pretty soon. We have support for Windows, Linux, Android, and then we have iOS and ORT web support coming pretty soon. So with that, thank you, everyone. And if there are questions. Go ahead. Yeah.
Actually, I'm going to read the question.
Sure. Sure.
So the WinML wrapper focus seems to be like vision. I use the example, vision. Any plans to build in a sequential data variable length? And specifically, what we are trying to do is text-to-speech software, and that's where it's not sequential data.
So let me repeat the question. As I understand, the question is are there plans to text-to-speech for on-device training for sequential data?
Yeah, I mean, all the examples I saw today, and even the WinML wrapper seems to focus on vision.
So on-device training is not restricted to vision. We do support speech along with images. Text-to-speech, there's no restriction in terms of the task itself. So if your model is supporting text-to-speech, you can bring that down to on-device training. It's mostly around the last couple of layers of your model that you will be training. And as long as you are able to train that offline and create a text-to-speech model, you can bring that down to on device, and then you can train it also. It's just that the examples to show vision is more appealing to a large audience, but it's applicable to text as well. Yeah. Yes.
Oh yeah. So this is an online user's question. So there are actually two questions. First one is the on-device fine-tuning done online, or first fine-tune and then use the personalized model?
So the So is the fine-tuning done online, or you first fine-tune and then use the personalized model? So there are two stages. One is the offline validation, where you essentially prepare the model, get it ready so that you can deploy it. But there is a phase of validation online where you make sure your model is ready for production testing. And then the actual fine-tuning, where you use the user's data and you tune the model to make it ready for inference later on, is done on the edge. So that's why the data never leaves the device. All of the tuning happens on the device. There was a question in the back, yes.
I was asking whether all the training node operators has to be explicitly defined and included in the ONNX operator set. So what if I have some very special data pre-processing for the training framework, and it cannot be represented by those ONNX operators, specifically ONNX training operators, how am I going to deal in this particular scenario?
Sure. So the question was, what if I have special training operators that are not part of my ONNX inference model? How am I going to deal with it, right? So you do not have to have the training operators in your ONNX model. You start with an inference ONNX model. And then when we have the artifact generation phase that Beju had mentioned, that's when the training graph gets created. So potentially, most of the operators, standard operators for training, will be available. However, if there are instances where you have a special model, you can reach out to us and then we can get that added into the system. But we don't expect a training graph to be present in the beginning. Yes.
Are there any power consumption measurements?
Sorry, I didn't get that.
Are there any experiments done on power consumption on edge devices?
We are in the process of, and we are having a multi-part blog series that's being released. We are in the deep dive stage right now, but we are also going to release the measurements for both performance and battery, as well as memory requirements. So we'll let you know soon. Yes. And the question was there any power measurements done? Sorry about that. Yes.
Yes, one more online question. This is by the same person. He asks, it reads, also, I'm very curious about the federated learning use case. How would a custom model incorporate the weights from other custom models, in bracket, all originated from the same ONNX model?
So I'm not going to delve into the details. So the question was, how can we talk more about the federated learning use case? I will share some resources. The federated learning is work done by Microsoft Research, and there are other companies as well. But essentially, we transferred the model weight differences back to the cloud rather than sending any of the other data-specific differences. And that's how the global model gets updated. I will share some resources maybe in the Teams channel, and then they can look into it further. Yeah. Thank you so much. Thank you, everyone.
Thank you, Shana.